This example you can find in the student paper. I want to use this example. We have process, actuator and sensor as a model defined with 3 PT1s. Note, in our cruise control we have only 1 PT1, temperature control 2 PT1s. This is a 3 PT1 example, and in a 3 PT1 example it is not so easy to calculate with transfer functions. The time constants are given as 0.3, 0.2 and 0.05, and then this system should be controlled with a simple P controller. And this simple P controller has a given gain of factor 10, which is 20 dB. So first we look for the Bode plot of the open loop, and then we add a negative feedback and look for the Bode plot of the closed loop. I will do this first for some points in a table, and second I want to show you this in my simulation program Chap, which gives the same values. Okay, if we just look for the Bode plot drawing, here you see some hand sketches of in the student paper. We can of course draw the Bode plot manually by using the approximations. At 3 PT1, the system contains 3 times the Bode plot of a PT1, and we have to add these. Note that the magnitude curve of a PT1 is has a horizontal part for low frequencies and minus 20 dB over dB part for the high frequencies, and a corner frequency point with the inverse of the time constant. So look, time constants are 0.3, inverse is 3.3, 0.2 inverse is 5, and 0.05 inverse is 20. These are the corner frequencies here in these sketches. And if we and the horizontal part for all blocks are at 0 dB. If we add them, then we have a 0 dB sum here. Then at each of these corner frequencies a gradient minus 20 dB, here minus 40, and here minus 60 dB. And finally we have to add the 20 dB K value. So this distance here is 20 dB, so the 0 dB line is shifted 20 dB into the negative region. So this is the possible hand drawing with approximation curves, which gives very good indication of the closed loop, of the open loop magnitude curve. Of course, you can calculate exact values of the magnitude. Here you have the equation. This is the tan, and you have 3 times the Pythagoras equation. For each PT1 you have a square root of real part plus imaginary part squared. So you see 3 times this square root function. The phase value is just 3 times the negative arctangent of the omega t values, with each the special time constant of the 3 PT1s. And I have done the calculation at 4 frequencies. You see, this is very small frequency, very high frequency, that are radian frequencies 1 per second. 0.1, 1, 10, 100, and the equations here and here give these values and phase value, open loop, and these magnitude values converted into dB values can be found in this column. So the left part here is the open loop system without negative feedback, and these values then are calculated with the Nichols equations, exactly with the Nichols equations. So here you get the magnitude value in linear, and here the magnitude value in dB value, and here the closed loop phase value. Now we just look for the approximations. You see in the case of low frequencies we have a high gain. This is 20 dB. Independent of phase, the closed loop should be 0 dB, and I have predicted that the gain error is less than 1 dB, and you see exact values negative 0.8. This is smaller than the predicted plus or minus 1 dB change. So our approximation number 1 is valid. So the 20 dB gain in the open loop gives a nearly 0 dB value in the closed loop system. Same is with very high frequencies. Here we see a very small value of gain, negative 50 dB. Independent of the phase, the closing of the loop has not really an effect. There is no change. Very small change in the third digit, small change in the dB value, and a small change in the phase value. But really, if the gain is very small, then of course the negative feedback has no influence. Look here at 10, the behavior is not fitting to our both approximations. The dB value is 2, nearly 0. And you see the closed loop magnitude is larger than 2. There is a 9 here. There is just a large gain. We have here a resonant effect. The phase here is a large negative that leads to a resonant effect here in the closing of the loop. I think it could be good to show you this Bode plot behavior in a simulation. So let's start my simulation program and type in these values. So C#, just adapting the size to my recording area and switching to English menu, and then P block with gain 10. Then 3 PT1s, first, gain 1, 0.3, all have gain 1, 0.2, and third one, gain 1, 0.05. This is the open loop system. We connect them with branches. Before we close this, we can now look for the Bode plot of this system. We start the Bode plot calculation with this button, and want to see the output block number 4. Output of 4. Of course, we can calculate any output of any block. Input is only 1. Starting frequency is 0.1. Is so far okay. We ignore at this time the phase curve. We only want to see the magnitude curve. And here you see, starting with plus 20, this goes down to 0 dB in the region shortly after 10. And here we have this 100 value. Note that this 100 value minus 50 is exactly, now we can check if we can find back the values from the table. I just switch to the table, look for 0.1. We have 20 dB here, negative 3 degrees, 20 dB, phase ignored. At 1 we have nearly 20 dB, at 1, unchanged, nearly 20 dB at this point. Then we have 10, 2 dB, 10, 2 dB, this point, and finally 100, negative 50 dB. 100, negative 50 dB. Okay, now this program can calculate the next curve. I store this curve. Yeah, and now go into the diagram and add now a negative feedback. So I need a summing point here, branch here, and a feedback connection like this. And I should not forget the minus sign. And of course, this is not an open input. If I click on the Bode plot, you will see now the program has analyzed the new circuit, the new signal block diagram, and find a new open input, and this is now called the 71. 71 is now the desired value input. Block 4 is the output, so here is no change. And if I recalculate this curve, then you will see the closed loop transfer function. This is a red curve, and you see here, yeah, open loop large, closed loop near 0 dB, open loop small, closed loop is exactly unchanged by the negative feedback. And here you see the effect in the near of the crossover frequency. Here is a strong resonant effect. The maximum gain here, we can say, is 14 dB. That's factor of 5. That mean what does that mean for a closed loop system? In this, if the input is this frequency, then you lost the control, because then the output is not equal to the input. That means 0 dB. The output has an amplitude which is 5 times larger than the input. That is not really that what you want. But you can't see this real behavior with the Bode plot. It's not so easy to interpret this Bode plot. These resonant curves are not good. We don't want to have them. But better is if we see this in the reference step response. If we look for the reference step response, adapt this window to my recording area, then we of course want to see output block 4. So time range, I don't know, we just have a unit step function here, and you see, okay, so what happens with my reference step response? There is a strong oscillation, low damping. Yeah, in our situation we have not a good curve. Normal curve goes up and want to finalize, reach the final value very quickly at 1. This controller caused a strong resonant effect in this loop. So this is not well designed control system. Worse than that, now I store this and fix, close the step response. Now we make the next step, and I want to show you what happens if we increase now the gain. The controller here can be changed by clicking the right mouse button, and now I just double the gain and look what happens. First we want to see the Bode plot. I think open loop is not so interesting. The open loop Bode plot is just this blue curve shifted 20 dB higher. Can do this, but then I have to remove the feedback. If I now store this and fix and recalc, we will see the new closed loop function, and you see, okay, the resonant peak is a little bit higher. This is of course higher because we have shifted the open loop with 20 dB higher. So no, not 20 dB, factor 2 is 6 dB, 6 dB, this is 6 dB higher, yeah, not 20 dB, 26 dB. Independent of this looks like a system where the resonant peak is a little bit higher, so the damping is a little bit smaller. But what we cannot see in the Bode plot is now we have an unstable loop. This cannot be seen in the Bode plot. The Bode plot can only calculate amplitude ratios of sinusoidal signals. In a Bode plot, the information that now my loop is unstable cannot be detected. So Bode plot information is often very good, but Bode plot contains some information that doesn't contain some information. I show you this just by calculating here in this case the step response of my system. If I do this, note what happens. I have now here a scaling. Yeah, look, for 300 there is small oscillations, and now you see the oscillations increases dramatically, so the system explodes, or I think it is clear this closed loop system is unstable. You lost the control. If the input is set to 0, the output will oscillate further on. So this is a typical case where you can see closed loop systems with negative feedback could also be unstable, and this it could be a danger in closed loop systems. It is just a disadvantage. If we have feedbacks, then of course this feedback could fail, and the system could lose the control. So we need some mechanisms, some investigations for the stability, and that is the next big chapter. The chapter 4 will start now. That is just the transition to chapter 4. I will show you some methods with which the stability of a system can be investigated and proven, so that your system will be get approvals to be used in situations where instability could cause damage or could cost lives of human beings, and then of course stability must be proven. This will be chapter 4.